Do you want me to? Oh, perfect. Beat me to it. Wonderful. Good afternoon, everyone. Welcome to the April 25th edition of the Ham Science Thursday afternoon Telecon. I know we've got at least one thing on the agenda. Mary Lou, hopefully, is going to continue our lesson from last week. Hopefully, everybody did their homework and we can discuss some of the answers and results. Is there anything else anybody would want to put on the agenda today for when she's done or beforehand or whatever? Any burning questions about ham science? No, okay. One other thing I just wanted to explain really quickly too is, as we've gotten past the eclipse, and a lot of us have participated in creating data, and we saw the Bill Engelke's wonderful graphs of some of the early results from the SEQP, and I think a lot of people might have noticed the 52 million data points that went into generating those graphs. And that's, of course, fantastic. That's far, far more data than we had even in October and way more than we had in 2017. What I suspect, and maybe I'm alone in this, and if I am, that's okay, but if there's others, we know that data is out there. We get kind of curious of like, okay, it was collected, but where did it go? How does it get stored? Where does it get put off into the future? So it's there for researchers well into the great beyond. It just since we all had a hand in generating, I guess I'm kind of interested to know about where it's going. So if there's other people that have that same interest, maybe we can find somebody to speak on that subject for a few minutes on a future call. I'm not sure.
Maybe Nathaniel can say a little bit about it now.
That'd be fine too.
Sure, I can say a little bit about it now. So
sure, go for it.
Okay, so the data is all going into different places. All of the data, if you participated in RBN, like if you made CW QSOs during the SEQP, if you used PSK reporter, so if you used FT8 or Whisper, all of that data is being observed by the reverse beacon network, PSK reporter, and the WhisperNet websites. All of those websites are owned and operated by independent groups that is not HamSci, so they're their own independent entities, but they make their data publicly available. The data, one of our collaborators on the HamSci side, Bill Engelke, at the University of Alabama, he goes to each of those websites and he grabs the data from all of those websites and puts it all into one database. He also takes that data and he will make sure that there's a latitude and longitude attached to every call sign, which he'll get either from information from the spot itself, like in the case of WhisperNet, or if necessary, he will pass that, he'll do a lookup on QRZ.com. Currently, his database is being stored on the University of Alabama's servers, and it's not yet publicly available, but we are very actively in the process of putting that aggregated data onto a publicly available repository hosted by the MIT Haystack Observatory, and that's called the MIT Madrigal database. That database, that will hopefully go live by the end of the summer, maybe even sooner. They're like very actively working on debugging this process and trying to get it up there. And we have a funded effort to actually put that on there. So it will happen. In that process, when it goes onto the Madrigal database, the summary plots, like the ones you saw showing the Eclipse bump that's on the front page of hamsci.org, those will be generated every day from those databases automatically in the Madrigal system. And once it's up there, anyone can go to the Madrigal system and download the data directly from Madrigal, or you can write codes in Python and you can pull it that way. We have software up on GitHub called the HARC-plot, the HamSci Amateur Radio Communications plotting code, that will generate both those summary plots as well on your local machine, or you can use it to to make subplots of the data and do more analysis. It's all free open source software, so people can download the data, run it on their own machines. It's not necessarily user friendly. It's written by scientists for scientists, and that's not to be exclusive or anything. It's just, this is the amount of time that we have and what we've been able to do so far. And we are very happy to help people learn how to use the codes to the best of our abilities, and share that information with you. So that's where that's where the majority of the data is going. If you participated in the GRAPE experiment, or the personal space weather station experiment, that data is either going up to up to the University of Alabama. They have a database at psws.hamsa.org that the data uploads to. If GRAPE digital RF data, that goes there, magnetometer data, that goes there as well. And you can download the data publicly there. If you're running a GRAPE 2 or a GRAPE 1 FL Digi, right now that data is going to the WWV Amateur Radio Club server. But soon, the GRAPE 2 data, we're also working on getting that, the full data set up to the University of Alabama server as well. So that'll be available through there. And then the logs for the solar eclipse QSO party, we're still working on scoring and processing them, but those will also eventually be available. Is that good?
Nathaniel?
Yes, Ron.
You mentioned something called Madrigal or Madrigal or something like that. What is that?
So it is a medieval choral group or a type of medieval song. so originally a madrigal is a form of like medieval song.
Right, which threw me when you said madrigal. It's like, okay, I'm gonna look dumb and bite. What is it?
So I don't know how they came up with the name of this, but the MIT Madrigal, and I should find out, and I'm sure they have a reason that it's called this. But I'll put the link in the chat here. Okay, actually, this is a good link because it explains what it is.
Okay, thanks.
So it's the MIT Haystack Observatory Madrigal database, which you can, whoops, that's my homework. It's screen 2. Okay, do you see that?
Yep.
Okay, yes, so this is a database where they keep geophysical data from the incoherent scatter radars, the GPS systems, and now it also the ham radio data is also going there. So as of 2019, they had over 27 terabytes of geospace data in there, and you can go to their website, cedar.openmadrigal.org. There it is. It's a very basic looking website, but you can access all of the data through here.
Thank you.
You're welcome. Back to Net.
So Nathaniel, do we all have to learn how to sing 4-part harmony to use it?
You'll have to ask Phil Erickson and Bill Rideout and those people that. I think it might be acceptable just to listen to madrigals while you use it.
Can my wife take my place for the 4-part singing and I still get credit for it?
That will be just fine.
Anybody in the household, right? Even the dog, right?
Even the dog does better than me, Mary Lou.
That could well be, yeah. I remember having a musical dog at a friend's house, and we would try to play music. The dog would howl. It was awful. Any rate, okay. So let me try to teach you some more things today about the scientific method, and then I'd like to start an experiment today and have people really do something with real data by next week. And I'm sure I'm not doing this very well, but at any rate, I'd like to try something like this. So this is called exploratory research. It's the sort of thing where you discover a door to a room, and you go in the room and it's all dark and you have a little flashlight and you just shine your flashlight around the room once, you pick one thing, you write it down, and you go into the next room. And then you let somebody else who knows what they're doing come in and do the real work. Anyway, so we're gonna see what we could do with our small flashlights here. All right, so I'd like to share my screen and have a PowerPoint. Does everybody have their homework ready? Let's see.
I emailed my homework to you, so.
Yes, and I never opened it. So there we go. Can't see how to get this thing to start. Make it bigger. There we
I
go.
think if you want to start it,
I
can you
do.
just press, you can press F5.
Oh, let's just
Or-
do F5 then.
You might have to press FN F5.
Sorry.
Or you can click slideshow up on top.
Yeah, see, I can't get to slideshow. It's behind things.
Oh,
It's too
well
big.
then on the bottom, do you see where the zoom is? And there's a little minus sign?
Can I make this there? I just got it to make it smaller. So slideshow from the current slide.
Great.
There we go. Sorry about that. So here we have, today is going to be more about the scientific method and some exploratory ham science projects. So from last week, one of the things we did was we found that the Doppler shift observations on that big plot from the internet, which was on spaceweather.com from Christina Collins, said that the Doppler shift observation indicated that the ionosphere bottom was receding upwards and then returning earthward at 67 miles an hour during the total solar eclipse. All right, I just love that number. My car has gone that number many times. Is this a speed of something physical moving or just an apparent speed of an image moving? What you think?
Well, I thought last week that we had talked about how it was the state of matter changing rather than the physicality of the matter moving. Was I wrong, or
You were
we
right.
talked about
You
that?
you just right on there.
I
So
agree with that.
yeah, so it's not a real physical speed. There's no something with mass. There's nothing with mass that is moving along at 67 miles an hour. It's an apparent speed and it's an image which is moving. So I like to think of it as, suppose I had my flashlight and off in the distance somewhere was a big white screen or a white building, and I could take my flashlight and make a spot on the building, and then if I went whip really fast, I could make the image of my spot whip along the building at faster than the speed of light. Because all I have to do is just change it a little bit right here, and it goes whipping along a big far away place at more than the speed of light. And so that's not possible. Einstein told us, and was very convincing, that nothing could move faster than the speed of light. But an image can. Or in fact, if you think about having a big white building far away, and you have, you're just going to project with like a slide projector. Does anybody remember those? Two spots, and you turn it on, it goes 2 spots, and they appear at the same time on the building. And then you said, oh, well, it was one spot that moved to the other building infinitely fast. It's not a real thing. It's an apparent speed.
Well,
So
in wave propagation, that's phase velocity.
yeah, okay.
Group velocity is below the speed of light. Phase velocity can be above the speed of light.
Okay.
Another thing is the 67 miles per hour is the rate that the path is changing, not that the actual effective reflection point is changing.
So with the reflection, the path is going
Right. By geometry,
at
the reflection point would be could be effectively traveling much less than that. But the effect to the path length is that number.
yes. And you told me that last week and I forgot it. Thank you very much, David. That's absolutely right. So it's, you're going in the slow lane then, right? Okay. What? And then we have the toothpick experiment. I hope everybody did the toothpick experiment. I had visitors to my house. Anybody who came in had to throw at least one group of 5 toothpicks on the table. And so their numbers went into this as well. I eventually got up to 100 toothpicks in bunches of 5. And in that, I counted 33 times in which toothpicks hit one of my 2 horizontal lines. So my final ratio, and I can't spell here, my final ratio was 100 divided by those 33, and it came out to be 3.03. And if you look at this graph I made of the number of throws is across the bottom, 5, 10, 15, 20, and the number that hit the line was then toted up. And then I did the division. I did the ratio, which is on the y-axis, the number thrown divided by the number that were on a line. And that came out to be 3.03, and it converged. It really did not wobble all over the place like throwing dice or anything, but it really seemed to go up and ended up at about a little over 3. Now, I want to know what other people saw with their toothpicks.
After 30 throws, mine came down to 3.
So you had 30 throws, you got 10 of them that were on a line, and so your answer was 3.
After 100 throws, I wound up with 28.
And so what did the ratio come out to be?
That's almost 3.
Okay.
Between 3 and 4, 3.5.
I'm so happy we're all getting the same answer.
I
Nobody
had
had 17 or anything bizarre, did they?
20 throws and the average was 2.22.
So we have
And,
numbers.
and it varied from 1.8 to 2.3 individually with each 5, but the total average was 2.22.
Okay, so we have a 3, a 303, a 35, and a 2.22. So it's sort of 2Z, 3Z. Has anybody got another ones? What everybody else got?
I see in the chat, Ron got what, 17 out of 100? There's your outlier.
There you go. Okay. Okay, anybody else?
So does that make Ron's ratio 1.7? Did I interpret that correctly?
Are you talking about mine, Gary, or another Ron?
Oh, no, sorry, the Ron Kuman, the Kettering Ron.
Thank you, because I was looking at my results and I was scratching my head going, okay, this is pretty basic math, pretty basic algebra. What is Gary seeing that I'm not seeing here?
Somebody else named Ron. Oh, dear.
No, that would be 5.88.
Yeah, about 6.
Okay. I don't know. So I would ask you, so we're going to talk about this results and then say where I found it. I'd heard about this thing since I was a child, and there's a nice version of it at the Exploratorium, which is a science museum in San Francisco. So if you look at toothpicks and Exploratorium, you're going to find this one, and they have a video of somebody throwing toothpicks. At any rate, we should have a road trip and all go there and see how they do it. At any rate, if you do it really well and carefully and nicely, the answer will converge to somewhat above 3. Should be 3.1. Anybody get 3.1? I did not quite get there, but I'm on the road to it. Actually, it should converge to 3.14.
14159.
That's it. That's the one. Yes. Yes. And I remembered that from that number, at least that far, from high school, because I went to a real techie sort of high school. And we had a good football team, though. And the football team, one of the cheers that we used was 3.14159. Block that kick and hit that line. There you go. any rate, so much for Ohio. Anyhow, so we got roughly that. Maybe you have to throw 1,000 of them to get 3.14, but I don't know. But let's assume that the numbers did come out to about that. Certainly 3 or 4 of us got 3 point something. So if this toothpick experiment converged to 3.14, what does that tell us about our local universe? And I know most of you are not astronomers, but
We're going in circles.
well, that's true, but that's not what this should tell us.
It has to do with the possible rotations.
No. It does not have anything to do with motion.
Is
But
is gravity involved?
No, no gravity. It has to do with geometry, which is where 3.14 is very useful.
Well, I mean, the
Is it a
different
spherical Earth?
orientations that a toothpick could come down at.
Unpredictable.
So there is a bit of randomness in
Looks
here.
like it has to do with the spacing you pick between the lines and the length of the toothpick.
Yes, that's very important. It has to
I
be
think
that
it's geometry, like you said.
right. So if you really, so something else, if you really want to know why this particular experiment comes out like that, if you go to the Exploratorium, they do have an explanation, but it was very long-winded and confusing to me. But it does have to do with, something about circles, which is where 3.14 comes in. So what is 3.14 defined as in relation to a circle? Steve, do you know?
Yeah, it's the ratio of the circumference to the radius.
Yeah. So how much around by how much across? And that ratio is 3.14. So I think this
Actually,
is,
to diameter, not radius.
Okay.
yeah, twice
Right.
the diameter. So what this tells us is that our local universe is flat. If you have a piece of paper and you draw this a diameter and a circle, and you take the measurements and do the ratio, it comes out to always 3.14. All right, so our local universe is flat. But now the question would then go further, is the whole of our universe, or the bigger part of our universe, Euclidean flat as well? So one should have to do this experiment again with a bigger piece of paper and therefore a bigger toothpick, and see if the ratio did come out to 3.14 as well. And you can think about this. There are models of the universe, the whole cosmic universe, in which the universe itself is not flat, it is curved. And the curvature of the universe would make the ratio of the diameter to the circumference not 3.14, but something different. So I want you to imagine this. Imagine you had a universe that was curved, like the top half of a globe or something like that. And suppose you stood at the North Pole and you had a piece of paper and you made a diameter and you made a little circle and it comes out to 3.14. So then suppose you make a really bigger circle. All right. If it's bigger, and your paper goes along space, then you'll find that the circumference is going to be a smaller number than if it were really a flat piece of paper, flat piece of paper. It's going to be curved down, it's going to be a smaller number, and yet the diameter would start out where it's not curved at all and go into where it's curved. So that would stay more or less big. And so the ratio would come out more like 2 rather than 3. So this brings up the question of how could we measure big circles and big diameters and see if our universe is flat? But at least this experiment shows that pieces of paper on dining room tables is flat. So there. But it makes you think about cosmology, doesn't it? Okay. So there were quotes on the scientific method that I gave you, and I found some more. I'll make another sheet of quotes about the scientific method. Does anybody have one that they particularly liked. Is anybody a Mark Twain fan?
Did you find the Charlie Chan one?
Yes, and I put that on the original one. We could go back
That's
and
in his movie Egypt.
I thought that was great. A mist on your eyeglasses. Yep, obscures the data. Are you a
Yeah,
Charlie Chan?
I went searching for another Mark Twain quote. I came up with the older I get, the more clearly I remember things that never happened. Um, and I related that to your comment about writing code. Is comment your code and write it down. I found that in scoring, the QSO parties. If I didn't write down what I had done for the October version, I might do the April version differently, and that, of course, would be a bad thing. So,
Yes. Yes, one should write things down, not for some student who's going to use it or other, but for your own very own self. Just you guys wait. Anybody have another one they liked? I'm going to tell you one at the end today, which is another one by Eddington. Anyway, so we go along. So another question was, which hobby taught you about the most about the physical world? And so I thought I would tell you about two of mine. I am a musician, and music has taught me a lot about the world, especially about thinking about frequencies. And I often hear things in, or imagine I hear things in frequencies and like to think about that. I like the frequency domain as much as the time domain. And so that makes Fourier transforms especially interesting to me. So I like music, and Steve Serwin knows about that. And then the other one is something that I did that perhaps would be different from most of you. I did a lot of sewing. I made my own clothes, sort of thing, and that was really useful to teach me about three-dimensional visualization, because you have to look at a flat piece of brown paper and imagine how if you cut it here and there and sewed it here and there, it came out to be a shirt that really fit you. So I got really good at three-dimensional visualization, and that's helped me a lot in physics and astronomy. So what anybody else do?
I played a lot of football when I was a kid.
Football.
Force equals mass time acceleration.
Oh my golly, and mass is important, isn't it?
Oh yeah, bigger you are, the faster you're running, the more it hurts when they hit you.
I've seen close up occasionally football players. They're enormous people. And I think, boy, I'm glad I'm not running around with them. Anyhow, oh yeah, football's a good one. Anybody else got another one?
Oh, how about gardening? That essentially so many things are cyclical in nature.
That's true. Oh yeah.
I've got one a little different. I was a traffic homicide investigator and crash reconstructionist, and I worked with a lot of formulas on vaults, flips, and rolls, crash depth, basically crash or crush depth, coefficient of friction of the roadway, speed, and light at night. For pedestrians walking across the road, and how fast the cars' lights would come up on them and illuminate them, and the driver could see them and his reaction time. I learned a lot about the physical world through being a reconstructionist.
How did you get into that business?
I was in law enforcement and in Tampa, and I was a Hillsborough Sheriff's Office, and I got into the track of crash investigation, and I decided that I wanted to eventually work for the NTSB because I like working crashes. So I was sent to the University of North Florida in Jacksonville at IPTM for the Institute for Police Technology and Training, and I was trained as a reconstructionist and for commercial vehicles in Florida, boats, and even light aircraft and passenger vehicles. So I got all involved in that.
Wow.
And it basically, just took several years to get trained, and worked over 400 vehicular homicides and what we call preliminary homicides, where they die within a year from the injuries sustained in the crash. And our department in Tampa Bay area was large enough that whenever we had a small, my wife was an air traffic controller, she calls them bug smasher aircraft. Whenever aircraft would go down, we would go to the scene, secure the scene until the NTSB arrived. But at the time, we would also assist the NTSB with the crash investigation, even though we weren't part of the official report. It was still something that they allow us to do, and it was quite interesting to see, how numbers come together, and it was an interesting experience. And I did that more than I did actual law enforcement. That was my job. I was a like I said, traffic homicide investigator and crash reconstructionist, and that became my full-time job in law enforcement.
Wow.
And that's all I did was work, basically wrecks, crashes, and things of that nature. But it was really, really interesting. We were also trained as crime scene investigators. We did our own crime scene collection and photography, crime scenes photography. One of the ones I liked at night that was interesting with the physical world interacting with light at night was when we take photographs, we would call paint by light. We take a camera and open it up for a long exposure, and then walk around with a bright, what we call a Kel light or bright flashlight, and shine it all around the crash scene, all around the vehicle. If it was like a head-on collision or something, all around the vehicles, you'd walk all around, shining the light on it. And then when you would go ahead and finish with the camera and bring up the photograph, you would see the vehicles illuminated by light, and just looks like a moonlit night, and the cars are all lit up, and the area around it, wherever you shined a light, was painted. It was there. And the cool thing about it is it never captured the person holding the flashlight. You never. I had a camera on the tripod and walked around and painted by light. I would see all those scene illuminated, and it would be really cool the way it would look, and you would see everything at night in a photograph that you normally wouldn't see with your naked eyes by looking around unless you had a big flashlight or night light like they work with on the interstate. But it was kind of cool because I, as the person holding the light, I was not in the picture at all. And
You should have been in that picture, but you didn't
Yeah.
be seen. Yeah. So this is a wonderful technique, and it's something that amateur astronomers like to do as well. So you
Yeah,
go
or aurora photography. You paint the
Yeah.
person
right,
or
or you take
the
a picture,
scene
just
to
a
just get a
picture of-
little bit of it.
Yeah, a picture of the constellation, and then you put a boulder or something in the front of the scene just by painting it with a flashlight, and it looks really cool. Neat. Anybody else?
Hobby that did that for me was interest in aircraft models and otherwise.
Do you have your private pilot's license?
I don't, but I have flown.
Neat. Oh, gee.
But just aerodynamics teaches you a lot about the physical world.
It does, and gravity always wins.
I use golf as my example.
What do you want to say, Greg?
I use golf. You think
golf.
you hit it flush, but you don't know where the ball's going to end up.
Yes, and it's got those little dimples all over the thing.
Right.
What's that
There's
for?
lots of variables. You don't know what's going to happen.
Yeah. And then there's baseball, which is a fantastic scattering experiment.
Yeah, yes. So just tell you, my two grandsons one is just 2 and one is just 7, and they're playing baseball now, and the 7-year-old's learning to bat, but the 2-year-old is pitching. I think we got an athlete coming there. It's just amazing at 2, he can throw a ball pretty much where he wants it to go. So Ed, what do you want to say?
No, nothing. I just checking back in. So.
Oh, okay. Hi
Okay.
there.
Sorry. Hi
Okay.
there.
Moving right along. So here's some science questions. So we're going to start doing some real science, folks. Here's the science questions that Nathaniel wrote in the NSF grant proposal, which was in fact funded. So there's 5 of them here. We're not going to do all 5, certainly not today. But 1, how do dawn and dusk ionospheric variability as observed by the Doppler shift measurements vary with local time, season, latitude, longitude, frequency, distance, and direction from the transmitter? Oh my golly. Number 2, is eclipse ionospheric response symmetric with regard to onset and recovery timing? Kind of, sort of, but maybe not. Number 3, how similar is the eclipse to the daily dawn and dusk terminator passage, besides being somewhat quicker? 4, do we observe multipath high-frequency mode splitting in the post-eclipse interval that is similar to the dawn events? Number 5, how is the response different for the southward annular eclipse we had in 2023 compared to the northward total eclipse of 2024? So yeah, we're gonna have to do all of this, folks. Anyhow, so I would like to start with number 2, the eclipse symmetry. I think it is the easiest of these, and we're going to eventually do some on all of them, I hope. So this is your homework, but I want to talk about it. And Gary, we can send this PowerPoint to everybody who's come to these meetings, right? Or whatever. Okay, open a spreadsheet, I use Excel, to record your measurements in. Choose a name, something like, and mine is called Eclipse Doppler _MLW .xlss, and put this name in cell A1. So this is one of these things like comment your code, put the name of the thing in the first block to the upper left, so that when you print it out, you can see which one this came from. Okay, do not use MLW, use your own initials or something that you will remember. And then you have to do file save as. Next, skip a few rows. Always skip a few rows because there's always things you forget to put in the upper header stuff. Then write titles for the files that you will measure. All right, so I would like to have this sort of metadata for a particular source, a particular person. You're going to write call sign, latitude, longitude, grid square, town, and state, which you may have to figure out, or maybe even leave blank. And then in the next row, fill in the names for these. So call sign, W2, NAF, latitude, whatever, longitude. And these will many times be on the data that you download. So just write them down so you know what they are. Then in the next row, write titles for the observations that you will measure. This is what you are going to do, particularly yourself. Write down the frequency, 10 megahertz. I don't know. What was the transmitter that they were looking at? So it's people listening to stuff. WWV. How far are they? What is the distance to WWV to whatever town and state they are located in? What was the eclipse local time where they were doing this? So we're going to do this just eclipse stuff one day. We all know, April 8th, 2024. No other days for now, just that day. And then symmetry. And this is a judgment at this point. I'm going to write down for symmetry, yes, no, or maybe. Or something vague like that. And then mode splitting. Do you see, particularly as the eclipse is ending, so it goes down first and then up, and in the up part, do you get multiple lines of different kinds of modes there? I don't know. I haven't decided yet if I'm going to put yes, no, or 0, 1, 2, 3, because I haven't really looked at enough data yet. But this is exploratory, and this is where we're going to refine what we're going to do later. Okay. Distance to time transmitters. So a great circle distance can be found at this really useful place I found on the web, where you could use whatever you like. gpsvisualizer.com. And the three that we have people that have looked at are WWV in Colorado. Its latitude and longitude are 40.68 and minus 105.03. And it transmits at these various frequencies, 2.5, 5, 10, 15. Then there's CHU near Ottawa, Canada, and its coordinates are given there and its transmission frequencies, and luckily they're quite a bit different. And then there's WWVH in Hawaii. I don't know if any of our people observed that or not, but I'm just putting it down anyhow. And it's quite a bit closer to the equator. It's only 21.99. And it transmits at the same sort of things as WWV itself does. So there's some information to get you started on part of that. And then we're going to do data from grape observations. So for the eclipse asymmetry part from grape observations, the way I found to do it, and somebody could help me if there's a better way to do it, is I go to pswsnetwork.caps.ua.edu and then I log in. If you have never logged in, then you have to go register your station. You go to the top menu bar far to the right and click on register your station. And they want to know a nice username and password and your actual email. And then you click sign in. All right. And another good thing to do, I find, is to click save this password so I don't have to remember it. Okay, whatever. Then, once you're in the central control unit here, you click on observations, which is in the top menu bar, 3 of them from the left. And then there are 1,311 pages of roughly 10 files listed on each page. Yikes! There's way too much data here, but we're going to see if we can make a little pass at it and before the number crunchers come. Then there's too much, so you have to filter it down and pick something you really like. So you click on the word filter, which is below the top menu bar. It's on the left and it's pretty hard to see. So you find filter and click on it. And then it says, oh, what do you want to filter on? And you got all sorts of possibilities. So what I do is I click on station nickname and I scroll way down to W2NAF. Yay, Nathaniel. And the first one I'm going to show them is RX888. And then you click the word, yes, filter. Please filter for me. And it does it. And then you get the much fewer than the whole batch. And you get the things that you are interested in particular, you get Nathaniel's files. And you may have to go down because we're past Eclipse Day. Go down to find Eclipse Day. And the file name is in blue and you click on that. And then it says, it gives you some metadata and it says, do you want to download the data observations or do you want to download the plots? I want to download the plots. Okay. So the plots come up for an observation. You get 2 plots. One is this green one with yellow lines on it. And the other one is a white graph with blue lines on it. We'll talk about that some other time. But I want you today to look at the green plots like this one. And what I've done here is I've taken his multi-channeled ones. I have cropped and pasted the green ones that look good onto a Word document. So this here is a Word document in which we can look at them all at once, one below the other. So time runs across the bottom, the x-axis from 0 to 24 UTC, and then on the left vertical axis is the Doppler shift. So look at the green plots. Nathaniel Frizzell is in what state? Nathaniel, you may not answer. Does anybody know what state he lives in?
Pennsylvania.
Yep.
So you're gonna write down in your notes, PA, okay. His solar eclipse was roughly at 3:30 in the afternoon, EDT. What is the time difference to UTC? Anybody else live in the Eastern Seaboard region? Do you know?
4 hours.
4 hours.
4 hours right now.
4 hours. Oh my golly, 4 hours. Great. Well, we're a little past that. So 4 hours. So he saw the solar eclipse at what UTC?
1930.
Right. So 3 o'clock in the afternoon is already 12, 13, 14, 15. So you start at 15 and you add the 4 extra to it and you get 19. So 19 and a half UTC. Look at these graphs and can you find 19 and a half? It's way over in the right. Do you see anything just short of 20? Oh my God, yes you do. Everybody see the eclipse there?
Yep.
So that's something you should check whenever you go to somebody else's page. That's going to be, where the heck are they? And see if you got it to the right thing. So so what I want you to do is to pick some people and to look at their green plots like this. And of course it's the whole day. So we got sunrise on here as well, which is going to be interesting. At any rate, the eclipse is over on the right, like 20% in from 24 hours. Okay, we're going to look at the first one in particular right now. So the first one had all sorts of activity at the beginning of the day, and then it was sort of like just a straight line, and then it went ba-doop, ba-doop for the eclipse. Okay, here it is. So this is the top one, which was channel 1 on his nomenclature. And this is just the last bit. It goes 18, 20, 22, up to 24 hours UTC. And so we can see the eclipse there. It goes down, goes up, and comes back to the line. So one of the things that's interesting about this one is that the line itself is pretty straight. Some others have pretty wobbly lines, or in fact, the wobbly line has some sort of trend going down and trend going up, whatever. This one's pretty straight. So we would like to answer the question now, is this symmetric about the time of the totality of the eclipse? So we're comparing the downward bit to the upward bit. What do you think?
Roughly speaking, yes.
I think I'm going to write a yes for this one. Although it isn't quite symmetric, because if you look at the top going downward, it's got sort of a skirt that goes out.
Yeah,
That
no,
the first one didn't have.
Yeah,
The first one had,
the return to the basic frequency does slide down rather, yes.
I said slide is a good word. So egress is slidey. So I also have, I'm not sure if I wrote it in the instructions, but I always have on my spreadsheets, the last column to the right is comments. And it's a nice wide column. So I would write something about that the egress had more of a curve to it, or it was sliding, or something like that. Nathaniel, do you know what all these vertical stripes are due to?
I'm not entirely sure.
You could say, I don't know. That's okay.
I don't
They-
know.
They
Fine.
could be the time ticks. Those tend to splatter.
Okay.
That's a reasonable thought.
You mean like the verbal or the oh no, you mean Dave, are
I
you
mean
talking
the
about
actual time ticks.
Yeah,
I've seen that working with FL Digi, that it tends to splatter.
I
They are
count
pretty regular.
32 of them in 2 hours.
Hmm.
So it's missing every other minute or something like that. But if you look at sort of 21 hours, there's a set of 3 of them really close together.
Yep.
Maybe those are minutes and the other things are 2 minutes. 2 minutes is.
Or I think this is CHU, so it might be the long tone at the top of the minute.
I don't know. At any rate, if they were really, really nice, we just count them and use
I
them.
did
as
notice in some of
statistics.
the other graphs that they go away when the signal gets weaker.
So they have something to do with the signal itself.
It might be some form of overload on the
Overload of what? What do you mean by
of the
that?
receiver, front end of the receiver, or some processing component.
So an overload in your equipment itself, or
Right.
this person's.
It could be an equipment artifact.
Okay. Any rate, not particularly useful, but it might be useful in some day. So I thought this was kind of neat. Okay, so your homework for next week. Each person will find and measure 3 or even more observations of the eclipse day. So you should focus on something. So there were many parameters listed as, what does this thing depend on? Latitude, longitude, distance, time of day, color of hair, whatever. So I would like each person by themselves to think about what interests them or something, and to see if the symmetry has something to do with these things. So is it a more symmetric response like this one if the person is located at a southerly latitude rather than if they're located at a northerly latitude? I don't know. What about the longitude? What about the distance between them and the transmitter? I think that might have a chance to do something. I don't know, but next week we're going to look at any sort of trends that people have found on whether there is symmetry or not. Has anybody got any other suggestions? Anyway, there we go. So I would like to end just by telling you a story about Eddington. Sir Arthur Eddington, great astronomer in Britain, who was the Einstein before Einstein sort of thing. And something about the observations that Edwin Hubble had made about the recession of galaxies. So this all was 1920s time, and Hubble was one of the first users of the big telescope out in California. So what he and Milton Humason measured was the spectra of galaxies, and galaxies had been known for a long time to be out there. There were a lot of nebulae or fuzzy things in the sky, and it was only about that time, so 1925 or even a little later, so mid-20s, when people realized that these little fuzzy things in the sky were whole island universes. They were whole sections of stars that were enormous, as big as the Milky Way, but way, way, way far in the distance. All right, so what could these galaxies be doing? And Hubble and Humason measured their spectra, which gives you a Doppler shift and tells you that the 24 galaxies closest to us, like Andromeda and those, are moving in a random fashion. They're sort of shuffling around, either going away from us or toward us in no particular discernible way. But if you go further out to the next cluster of galaxies, in which you're going again 10 times further out than the size of our cluster, then you find that all the galaxies are are going away from us, and it more or less together as a group they're going away from us. And then Hubble looked at the next group of galaxies out. So when he did these measurements, he made a plot, a graph of the distance the galaxies were from us on the x-axis, and measured by various different means. And then going up on the y-axis was the speed at which the galaxy was either receding or approaching us. And his graph, I should have found it, but I didn't have time to find it, showed that if you started at 0, 0 near us, the nearest group of galaxies just are milling around. And then after that, it was a straight line going up, so that the farther the distance was, the faster the recession speed was, except for one galaxy, which was off the line. And in fact, it was quite off the line. It was down at a negative number. Eddington looked at that and said, Hubble, you're an idiot. He said, go remeasure that point. That point's wrong. Clearly, the theory is that the straight line goes up and everybody lies on the straight line. And this data point is just a bad data point. Go remeasure the bad data point. It doesn't agree with the theory. Sorry, it has to be thrown away. And so Ed Hubble was annoyed at that, but he did go and remeasure the point and realized he'd made a numerical error. Instead of minus, it should have been plus. And if you do plus, it did fit on the line. So that's where the theory corrected the data. I think that's hilarious. Anyway, okay. So I think that's all we got. We'll stop sharing. Does everybody know what their homework is? Go look at some of these green graphs with the yellow line going across, and at least look at where the eclipse is and is that part symmetric. But there's lots of other things to look at that green line too. It's time's up. Bye.
Wonderful. Thank you, Mary Lou. Anybody got any questions while we've got a few minutes here?
I wanted to ask something. So what was that mode splitting you said about? What is that mode splitting and how you hear it?
Who wants to talk about mode splitting? Nathaniel.
Mode splitting. Actually, I think Steve Serwin is the best person to talk about mode splitting.
Steve Serwin, talk about mode splitting.
Okay, can I share my screen?
Yes.
Yeah, please.
Okay. Mode splitting first. Okay, here's, can you see this?
Yes.
Okay. Here's like a 1-hop mode between a transmitter and receiver. Here is a 2-hop mode. As David pointed out, it is the path length change for one mode, up and down, for 2 hops, up, down, up, down. It's that path. When that path changes, that's what makes Doppler change. In fact, Doppler responds to the time rate of change of that. So here is a ionoson data for HMF2, height of the F2 layer. This isn't now, this was some years ago when the thing's a little calmer, but you can see at night, the top of the F2 layer is pretty high. And then here comes the sun, all the ionization kicks in. And like you said earlier, what's really lowering? It's not really atoms moving up and down. It's where in the ionosphere the ions are. Which atoms are ionized and which not. That's what lowers. So as the sun comes up and it burns down, this is what the height of the F2 layer does. You see this slope right here? That slope is what drives Doppler. So, okay, I showed you that picture of that I started with, this one here, and you can calculate these different things and take this data, and feed it through the different formulas. This is what the height of the F2 layer is. If you want to find out what those leg lengths are, here is how that translates to 1-hop mode. This is what the height is. This is H. This is the actual path length for 1 hop. This is the path length for 2 hops. Look at the difference in the height delta, and in particular, look at these 2 slopes. So when the sun comes up in the morning and the F2 layer lowers, this is how much 1 hop changes path length. This is how much 2 hops change path length. See how much more slope you got here? That's why there's more Doppler for 2 hops than there is for 1 hop. So you can actually take this, do it for more hops, and predict mode splitting.
So how does that look on the green graph with the yellow line?
Green graph with the yellow line. Green graph with the yellow line.
Yeah, the grape data that was being shown before.
Oh, well, what you have to do is take this data, take the time rate of change of it, so you can get this. This is a height change. This is for 2 hops, whatever those numbers are right there in height, and then divided by this amount of time. You could actually draw that as a straight line and that as a straight line. And did you see mode splitting in your, well, not on the Eclipse. I don't think we've got it in Eclipse run. We get this every single morning.
I saw it on some of those green things that Nathaniel had.
Yeah.
What you would see would be an S-shaped curve with a slightly taller F-shaped curve above it and a taller S-shaped curve above that, depending on how many modes you get. But that's why it happens. It's because, that's why I believe it happens, because when the height changes, it changes the paths of the different number of hops differently, and the ones with more hops change more, as you can see by this graph right here, in the same amount of time. So they're changing faster, and faster means more Doppler.
Do you ever see 3 hops?
Yes. In fact, I can show you a picture where there
You
are
can-
5.
You can see around the world hops.
Yeah.
Nathaniel, I have a question about the data. Is what was being shown there the DRF or the FLDigi data?
The green that Mary Lou was showing, that's digital RF data.
That's what I thought. So that shows you the full spectrum, whereas FLDigi grape data is just a single Doppler shift, correct?
That's correct.
So you won't see
and
the mode splitting in that.
That's right. The mode splitting will be obscured by the regular FLDigi type data.
And are both on that repository, or that the
So
Alabama
no,
data is just
the Alabama data is only the digital RF. The WWV-ARC has the FLDigi type data.
right, but we don't have access to it, do we?
Not so easily, but Christina does on a regular basis copy it over to a Zenodo repository, which we can get to you.
Okay.
And the eventual plan is that everything will be transferred over to, we're eventually migrating everything to a digital RF format. And there will be software that will let you convert digital RF into an FLDigi style data set.
So
But
what do
that's
we
for
have
another day.
available for this week is sort of my question.
Yeah, no, this
So
this
available for this week is the
digital RF.
the digital RF.
Okay, wrap it up, Gary.
You
All right, good.
you want
Well-
to see a little bit of the TDOA stuff?
I've got to check out of here in a few minutes, but anybody's obviously welcome. We'll leave the connection up.
Or can you show us next week?
Sure.
Let's do it next week. I got
Okay.
something.
But I can show you an Eclipse bump.
Sure, show us that.
There it is, right there.
That's beautiful.
Here's morning stuff. Here's Eclipse bump. That was on one band. Here's another one. This is Eclipse bump.
Wow.
So yeah, we saw the eclipse come by. We do have some analysis to do here because these points down here are too fast. So we have strong evidence that there is both E and F layer multipath, as well as 1 hop, 2 hop off the F layer. And so I've been doing those analyses. For example, right here, here's layer height right here. And by the way, you asked what they were. This shows layer height. This shows what the TDOA should be. And this is if it's 1 hop, 2 hop off the F layer. This is if it's 1 hop off the E layer and 1 hop off the F layer. They're much faster. And they're matching up. So what we're seeing is not 1, but 2 data streams going by here, because sometimes we had EF interference, sometimes we had 1 hop, 2 hop interference. And the algorithm that Tom used to make this one simply took the strongest. So these down here, these between 1/2 and 1, don't like those in particular. So we're still working on analyzing. That's why I asked you for the ray tracing, Nathaniel, is to figure out what modes they are. So not that one, this one. Just you asked the question, Mary Lou. If you look here, the TDOA before the eclipse started is around 1.7 milliseconds. Remember that number? And then the peak was about 2.19. So if you go to the graph here that converts those to layer height for 1 hop, 2 hop, The 1.7 here is 1.567. 1.7 is 275 kilometers, 275. And the 2.19 is about right here, is about 340, about 340. Okay, so how does that match up with what the Austin ionosonde thinks was happening that day? Where'd Austin go? Right here. Here's the Austin ionosonde. It did not show an eclipse bump, but during that time, before, the eclipse was right around here in time. So here's several hours before. What did you think the layer height was? 275 kilometers. So we were right on the money. Our TDOA gave this value right on the money. The 2.19 gave us numbers up in here, 300, 345, 350. Somebody was on the thread was saying that these ionosondes don't do well for things like eclipses. I don't understand it, but if you look, the Boulder ionosonde, it showed a bump. It showed an eclipse bump. We got good bumps from the Boulder one and the ones out towards the West Coast during 2017, but Austin has never showed one. But anyway, this place here where it's steady came out really good.
What's wrong with Austin?
I don't know. So this corresponds to the 275, this 1.7 right here. So that agreed. Austin just kept this thing flat, but we saw a very clear bump that went up as high as what the nighttime high was.
Cool.
So we're still analyzing the data. This is from the correlation analysis that Tom K1FR is doing. We had just one brief look last Friday of some of Alex's data, and by golly, the two plots of TDOA look very, very much the same. And that's always a good thing when you analyze things two different ways and it gives you the same answer. His is doing the chirp beat frequency method, and Tom is doing autocorrelation.
Steve, some comments on the Austin ionosonde. So the main person who was commenting on it was David Themens, and David Themens is a PhD space physicist up at University of New Brunswick in Canada. So he knows what he's talking about. He said that the Austin ionosonde, and I think Terry Bullitt might have said this too, is running an older version of the software that doesn't do automatic detection quite as well as newer versions of the software. That stuff can be manually rescaled. David Themens did do a manual rescaling, and he sent me those FOF2 values in a text file. I just sent them to you by email.
Oh, thank you.
And you can also feel free, you can ask David Themens more questions.
What's his last name?
Themens. I just forwarded you the email from him.
Okay.
Are we meeting?
Our preliminary results, you asked for a number. The number was 70 kilometers. But this is preliminary. We're still working on it. But the difference between this point and this point, this is TDOA, but that translates to about 70 kilometers if you figure it's 1 hop, 2 hop off the F2 layer.
We're good for meeting tomorrow, Steve, at 2 o'clock Eastern.
You bet.
All right. I have to go.
Okay.
Thank you, everybody.
Did anybody else want to see some stuff on modes?